In this first module, we're going to be introducing some concepts that we'll be going into in more depth later on in the semester. For starters, let's just talk about what's the nature of matter and energy. As the slides explain, matter is made up of atoms, which are composed of a nucleus with protons and neutrons surrounded by a cloud of electrons. The protons are positively charged, the electrons are negatively charged, and the neutrons have no electrical charge. In a normal atom, under normal conditions, the number of electrons equals the number of protons. And it's the electrons as the outer shell of an atom that determine the characteristics of that atom, that determines its color, its hardness, how it interacts with other things. Does it bind together with other atoms of a different type, for example, to make certain kinds of molecules? So whether something is red or blue or hard or soft or a liquid or a gas at room temperature or a solid at room temperature is determined by that outer configuration of electrons. Since the number of electrons equals the number of protons, we identify atoms by their type, called an element, based on the number of protons in the nucleus, which is normally equal to the number of electrons in that atom. So that's called the atomic number. That is just the number of protons in a nucleus. An atom of a particular type, such as an element of, say, carbon, which is got an atomic number of 6, and you don't need to memorize any of these numbers, has always 6 protons in the nucleus. If it's got 6 protons in the nucleus, that's a carbon atom. But it can have different numbers of neutrons in the nucleus. Those are different isotopes. That'll be important later on when we're looking at understanding the history of the Earth's climate. So that's the basic structure of ordinary matter that we'll be dealing with in this course, and we'll be coming back to that later, especially when we're talking about nuclear energy, which is stored in the nucleus in those protons and neutrons. Some of that mass is actually acting as a kind of atomic glue, and when the atom splits apart, that mass is converted, some of that mass is converted into an enormous amount of energy. What is energy, though? Energy is something that's oddly a little bit difficult to define because it can take many different forms. Very broadly speaking, you could define energy as a quantity in a closed system. Closed system just means things from the outside aren't interacting with what's inside it in any way. That's a quantity in a closed system that is always conserved, that never changes. That's the principle of conservation of energy. But energy can take many different forms. We're familiar with several of those. For example, a moving object, such as this pen, as it moves, that's got energy due to its motion. That's called kinetic energy. If I hold the pen at a certain height, it's got something I call gravitational potential energy because I don't have to do anything to it except let it go, and then all of a sudden it has energy of motion. That's due to the gravity of the Earth. I take a lump of coal or a chocolate chip cookie. Both of those have stored energy in the chemical bonds between the molecules and atoms that make them up that can be liberated through chemical reactions and converted into kinetic energy. That's stored chemical potential energy, and that's usually liberated through burning, which just means chemically reacting it with oxygen. As I mentioned before, there's potential energy in the nuclei of atoms. Light itself has energy, and ultimately on Earth, most of the energy available here ultimately comes from light from the sun. Plants convert that light energy into chemical potential energy through photosynthesis. Then we eat a plant, and then we get some of that chemical potential energy, which we can use to run around, kinetic energy. So energy is conserved in a system, but it can change forms. Some of those forms are more useful for changing the world around us, making a car move, making electrons move through an air conditioner to keep the room cool, pushing electrons through a TV so that we can watch a movie. And some of those forms of energy are not particularly useful, such as the heat that comes out the back of your computer when it's working very hard. Unless you're in a cold room, it's nice to have that extra heat. Otherwise, that's a form of energy that's not very useful and usually wasted. So we'll be talking not only about transformation of energy between different types, but also about the quality of energy and how useful it is. And in the book, in the slides, it talks about the concept of a flow of energy versus a fuel. And a fuel is basically going to be stored chemical potential energy, such as in food or coal, and also in like a uranium ore has stored nuclear potential energy. And a flow would be, for example, the wind blowing. I can put a windmill up in it, and that flow, I can capture some of that flow of energy and convert it to electricity. But if I don't, that energy just goes on by and I've lost it. That's the difference between a fuel and a flow, and we'll be coming back to that later as well.